Hello everyone and welcome to AWCI's webinar, Introduction to Rainscreen Walls. My name is Tanwin, AWCI's Education Program Manager. Before we start, a few housekeeping items. Mics are muted. If you have any questions, please ask the questions using the question tab on your dashboard. The slide deck is available in the Handouts tab. Our presenter for today's webinar is Denali Jones, Technical Director at Rainscreen Association in North America. Denali is an engineer focused on building enclosures. His work is concentrated on finding practical and performance-driven solutions to complex enclosure problems, ranging from high-rise office towers to hospitals, multifamily manufacturing facilities, and everything in between. He has extensive experience in all aspects of enclosure design, including roofing, glazing systems, horizontal waterproofing, below-grade waterproofing, and Rainscreen Walls assembly with just about any type of cladding. At this time, welcome Denali.
All right, thanks, Tao. Let's jump right in. So this is just kind of an introduction to Rainscreen Walls, sort of a 101 level presentation. So I can go ahead and skip through the AIA disclaimer. I think Tao covered that as well. So today we're going to be talking about really what is the building enclosure and what its purpose is, why do we need it. We're going to go into some definitions, make sure we're all on the same page with terminology. So what is a rain screen? What do we need to have a rain screen? We're going to talk about the benefits that a rain screen wall provides when we're trying to make a high performance building, and then identify the fundamental components of a rain screen wall. So what's the bare minimum that we need to have in order to call something a rain screen? Okay. So the building enclosure is sometimes called the building envelope or the environmental separator. It's really, it's what makes it a building and not just a structure. It's what separates one environment, like outdoors, from another environment, like indoors. So without the enclosure, we don't really have a building. We just have a structure. So the building enclosure wraps around the entire building. It's not just the walls and the roof. It's also the basement floor systems, the foundation walls, above grade walls, windows, doors, roof systems. And keep in mind that some parts of this enclosure might be heated, some might not be. You could have a ventilated crawl space, which is ideally supposed to be kept relatively dry, even though it's not heated. Same with a vented attic. So it may or may not follow the line of the thermal boundary, but the intent is to separate one environment from another. Now this diagram shows just a single family home, but you can apply the same principle to really any building. So you can draw a line around the whole exterior of the building, the envelope, and see where that's supposed to be. Okay, so like I said, separates conditioned, i.e. indoors, from unconditioned, i.e. outdoors. And the way we do that is by controlling the different environmental loads. So we're controlling bulk water penetration, which is really the main focus of the rain screen. But we're also trying to control airflow with the air barrier system, heat flow with insulation. We're trying to control water vapor diffusion to prevent condensation issues. So we've got our vapor retarder layer. Trying to control light and solar radiation, right? So most walls, obviously they're going to be opaque, but that's something to think about with windows and glass design, passive shading, all that sort of stuff. And then also, just controlling noise, fire, smoke spread, things like that. So these are all the different loads you might see on the building enclosure, and we need to control all of them, all right? And not only that, but the enclosure needs to be durable, maintainable. It's got to be constructible. Has to meet aesthetic expectations. It's got to look good. It has to be economical. Have to actually be able to afford to build it. So that's asking quite a lot, and there's a lot that goes into that enclosure design. So why do we want to manage water? Well, hopefully that should be fairly obvious, but there's a lot of good reasons. I live in the Northwest. I'm in Seattle, and we've learned a lot of these water control lessons the hard way. We had the leaky condo crisis back in the 90s, early 2000s. A lot of buildings were built with very poor rainwater control measures, and we had buildings rotting out all over the place, claddings that couldn't drain and couldn't dry. So it can have pretty severe impacts, not just aesthetically, but also it can actually impact structural integrity of some of these components. It affects indoor air quality, occupant comfort, and the ability to even live in some of these buildings. It requires early removal, replacement, disposal of materials. So this is what we want to avoid. We want to control water. That's the most damaging thing that happens to buildings, just in terms of overall dollars lost due to construction defects. Water is number one. So water control is really just, it's a balance, right? It's a balance of wetting and drying. You have to make sure that anything that can get wet is able to dry. So when things get out of this balance, that's when we see problems. All right. So buildings are always going to get wet. We can't control the weather. It's going to rain, and so we need to allow things to dry out and drain. Right. So a well-designed building enclosure has to allow water to drain out and to dry. So some materials are obviously going to be more sensitive to that than others, and that needs to be considered in our design. Okay, so just some examples. I already mentioned the leaky condo crisis in the Northwest. Lots of expensive failures, billions of dollars in damage and rehabilitation costs. So building codes tried to respond to that. There's some language in IRC and IBC about properly flashing and draining things, but it's not super. It's really just a bare minimum requirement. There's been a demand lately for more durable, more resilient, more energy efficient buildings, and so that's where we get into high performance design. And so this is where water management becomes that much more important. So this is why RAiNA was formed, is to promote the use of Rainscreen Walls, and there's really a ton of benefits. I would say number one really is just at the top there, the durability aspect. You want your buildings to last a long time. Managing water appropriately is the best way to do that. Resiliency, by that I just mean remaining functional in the face of environmental changes. So we're seeing stronger storms, more severe weather events. Just having buildings that are adaptable, that can handle those things is really important. Healthy, right? Better wetting and drying management. It's going to reduce the risk of problems like mold growth or other things that can impact indoor air quality. Energy efficiency, that's a big one. So we're seeing a lot of what we call Rainscreen retrofit projects. That's a great opportunity. When you're adding a Rainscreen cavity, you can also add exterior insulation. You can improve the thermal performance of your wall. Really easy to do behind Rainscreen systems. Safety, right? Again, better wetting and drying management reduces, impacts like rot, corrosion, things like that can actually create safety issues. And design freedom. We want to really promote this. Rainscreen it's not a particular product or a system we're promoting. You can have a Rainscreen assembly look like pretty much anything. You can design it around any type of cladding you want. There's all sorts of flexibility there. Okay. So how will we successfully manage water? Well, let's talk about how water gets in. So in order for water to get into the building, we need three things, right? We need a force, we need an opening, and we need water on the surface. And you have to have all three of those things at the same location for water to leak in. If you take away any one of them, then you're not going to have a leak. So forces, we're really talking mostly about wind, wind-driven rain, momentum, things like splashback, gravity, taking things down. Capillary suction, that's, small gaps and cracks that'll actually pull water in, like a head joint at a brick over a window, something like that. Lots of different forces. I should say the forces are really difficult to control. Most of the time we can't actually control them. So we just have to design around them. And same thing with water on the surface, right? Buildings are going to get wet. We can't really control that. I mean, there are some measures we can take, like adding overhang protections, things like that. But, with larger, more complex buildings, there's always going to be parts of it that are going to get wet. We can't avoid that. So we just need to design around it. So most of the focus from a design perspective is really just on managing these openings and not having them or minimizing them if we can. That's the big focus in design and construction. So lots of different approaches to rain control, and they could really be broken down into two different categories, right? And this works for like an assembly or even on a detail by detail basis. You can have a perfect barrier approach or an imperfect barrier approach. So perfect barrier, I don't mean is the perfect way to do it. What I mean is it relies on a barrier not having any flaws in it. So this could be like a face sealed system. A good example of this would be glass, right? Glass on our windows is a perfect barrier. It is face sealed in the sense that it is the outermost layer that you can touch that is controlling the water. Or the other approach is a concealed barrier. This could be like basically a old school stucco over building paper. The building paper would be your concealed barrier, right? We want that's our water control, and we want that to be perfect. Now, the imperfect approach is, again, not saying this is not a good way to go, but it's really it's giving us kind of a second line of defense, and so that could be broken down into drained or screened approaches, which I'm going to be mostly talking about, or mass or storage assemblies, right? So think like big, thick walls. This is how they used to build, way back in the day. Really just pile a bunch of rocks together, and that's your, that's like old castles and things like that are built like that. Just there's storage capacity built into the thickness of the wall. So those walls are allowed to get wet and then dry out, and if they're hopefully maintaining that balance between wetting and drying, that can function. So with drained or screened assemblies or details, that's where we have a cladding layer, and then a distinct cavity or drainage plane behind the cavity. That can allow venting or ventilation, and that's really what a rain screen is. So here's just some more examples here, right? Perfect barrier, I talked about, like glazing. That's a great example. Perfect barrier. Architectural precast. That's a perfect barrier. We're really expecting that water control to be on the outside face of that precast. Same thing with like insulated metal panels, or a lot of the old school EIFS systems didn't really have any backup membrane behind them. They were just face sealed, so that would be a perfect barrier. There's really no ability to handle water behind that outer layer. And then we get into mass storage assemblies, right? You got your rubble wall, just solid masonry, just multi-wide brick. Sometimes there's composite systems. You got a brick veneer over a CMU wall. Those are really intended to store and release moisture over time. And then what we're going to be talking about, lots of different ways to do a drained assembly. So you got your lap siding, got masonry veneer, just any kind of panel cladding system, things like that. So Rainscreen wall. So what is it? This is the definition that a bunch of industry experts came up with, and it's a assembly applied to an exterior wall which consists of, at minimum, an outer layer, an inner layer, and a cavity between them sufficient for the passive removal of liquid water and water vapor. So what does that mean? Also, there's a QR code. If you want to go there, it's going to take you to RAiNA's website. We've got lots of other defined terms and resources, which I'll talk a bit about later. So really, that's that's what we mean when we say Rainscreen, right? It's the outer layer, inner layer, and then the cavity, and it's sufficient for the passive removal of liquid water and water vapor. Okay, so just a couple of examples here, right? So we've got this pretty common assembly here. We've got some kind of cladding system, panel cladding system. That's our outer layer, right? We've got the inner layer, which is the WRB, water resistant barrier, that's over the sheeting. And then we've got our airspace in between. That could be formed by a bunch of different things. Here in this case, it's formed by vertical wood strapping or furring. And then you can see we've got this, the blue is showing liquid water is able to drain out of here, and then 5, that's water vapor. So this would be ventilated as well, right? So it's, there's a ton of different ways to do it. It's product, material, and building type agnostic. You can do it with any type of building, right? So we just showed the wood framed example. This is Rainscreen over a steel framed wall. We're in this case adding exterior insulation to meet the the energy code requirements. Typically with steel framed walls, you're going to be adding exterior insulation there. But again, you've got those same 3 components. You got the outer layer, you got the inner layer, and then you've got that airspace in between. Could be done over concrete or CMU as well. Again, the outer layer, the inner layer, and that airspace in between, right? So lots of different ways to do it. This is showing vertical hat channels for these 2 assemblies. This could also be clips or girts, things like that. So we'll get into more of those details later. But again, it's the same principles. It can be done with pretty much any type of construction. All right, so drainage and ventilation. So let's talk about how buildings get wet, right? So there's a bunch of different moisture sources, right? Number 1, precipitation, so rain and snow hitting the walls. Number 2, this is vapor movement. So this could be transported, depending on climate, either from indoors to outdoors or outdoors to indoors, depending on weather conditions, climate conditions, which way that vapor is going to move. And then number 3 is actually built-in construction moisture. I'm very familiar with this, working in the Northwest. It rains a lot when buildings are being built. You've got especially absorptive materials like wood are going to suck up a lot of moisture, and it needs to be able to go somewhere once the building's built. And then you've got number 4, which is groundwater, which we're not really dealing with much with RAiNA. We tend to stick to the above grade assemblies, but those are the 4 sources of water that can affect the building enclosure. Okay, so the ways that buildings dry out is also multifaceted here. So we've got number 1, this is evaporation, right? And this obviously greatly depends on the weather, the climate conditions, how fast or how slowly this happens, or whether it happens at all. And it could go to the indoors or to the outdoors, right? Either way. depending on how the wall is constructed and what the conditions are. The second one here is water vapor transported by diffusion, right? So that's again, that's kind of could either be a source or a way for buildings to dry, depending on the conditions, right? It can either move inward or outward. Number 3 here is drainage, which is what we're really concerned with RAiNA and Rainscreen assemblies. And number 4 is ventilation by air exchange, which is, again, that's also what we're most concerned with RAiNA. So we really want to make sure we have that drainage path and that ventilation by air exchange. So lots of different ways to get that airspace, the cavity. This one's pretty typical. It's you got your house wrap there, and you've just got vertical wood strapping or furring. Very common in multifamily construction. Starting to see it more in single-family homes now. But that's a great way to get that cavity. Just continuous vertical cavities through the wall there. You've got flashings at each floor line and window heads to kind of break that up. Another example more on the commercial side is steel girts or hat channels. Quite often will be attached to some sort of thermally broken clip or even just a thermally broken girt, but something to help maximize the effectiveness of that exterior insulation. And then we also see some engineered drain mats or composite materials, so either like an entangled mesh or a dimple board. A lot of those are commonly used in residential. You can put those up behind stucco or thin stone veneer. Some of them actually have lath built into it. Sometimes you put a lath over it. But that's another great way to maintain that drainage cavity. Right. So here's just some more examples here, right? So this is kind of the typical flashing profile we talked about. It's really important to work through not just the assemblies but the details, right? We see this quite often. This is the vertically oriented hat channel behind a panel cladding, right? But if we had, let's say, a vertically oriented cladding and we needed a horizontal support behind it, you can see here this hat channel is now actually going to block drainage. So that's actually not a rain screen. That will collect water there. Not good, not what we want. So that blocks drainage and airflow. A good way around that is to, you could use a profiled cladding. So water and air can get around that hat channel, or just use shims. Again, lots of different ways to do it. Or another option, they do sell perforated hat tracks, so water and air can get through it. Again, you got to be really careful about not just the assemblies, but the details, how all this stuff is going to be attached. Are we blocking airflow anywhere, or blocking drainage? All right. I also should just a quick note. You hear the term venting or vented or ventilated quite often, and they're sometimes used interchangeably, but they're really not the same thing. So the image number 1 here, this is what we would call vented. And what that means is there is an opening, right? But you could imagine, there's, you see that flashing is down tight against that cladding there below. So you can imagine this being repeated over and over again. So we have actually a way for water to vent or air to vent into this cavity, but we wouldn't call it ventilated because we don't actually have an opening at the top and bottom. This can actually severely restrict the amount of drying that can occur. You might get, maybe 1 to at most 10 air changes per hour in this cavity. Whereas if you have an image like we have on the right here, number 2, which is what we call ventilated, you actually get significantly more airflow, moving through this this rain screen cavity, which can help dry things out. So this could be on the order of 50 to 100 air changes, depending on conditions. So much more effective for allowing water to or air vapor to dry out of those cavities when they're ventilated. And we should talk about the actual size of the cavity you need. Right, so this is a common question we get all the time is, well, how big of a gap do we really need? Well, so number one, that would be like no gap. That's just the cladding directly fastened to the wall. So that's not what we want. That's no drainage, no airflow. Once you get into a really small gap, like a 1/16 to an 1/8 of an inch, that would be like something like a drained house wrap. That can allow some drainage, but really not any meaningful airflow. And then once you get into something on the order of like a 1/2 inch, that's definitely going to drain quite well. You're going to get pretty decent airflow as well. And then larger gaps, 3/4 inch and above, we've got lots of drainage, lots of airflow. So small gaps like we've got in number 2 here, they may actually stop capillary action, but they're not going to stop water droplets from actually bridging. What we call bridging is when water can go from the backside of the cladding and touch the inner surface, the WRB. Once you get into a larger gap like a 1/2 inch, then you're actually going to stop bridging. So water, if it's draining down the backside of the cladding, it can't actually touch the WRB. So it's just you're putting less of a load on your WRB. Once you get into really big cavities that actually can impact fire and smoke propagation, this is why we actually don't want gaps to be too big. Usually, 3/4 inch to an inch is fine in most cases, but larger than that, you start to get into more challenging fire considerations if you've got anything combustible in there. I will say that you don't actually need a 1/2 inch to drain effectively, but you see these larger gaps really for a couple of reasons. Number one is a lot of the materials that we use to create these gaps are either a 1/2 inch or 3/4 inch or 1 inch. So you're just going to create that cavity just by the geometry of the materials you're using, whether that's furring strips or a drain mat or something like that. You're not going to get it super duper thin. And the other is tolerance. We're not expecting these walls to be perfectly flat. We're not expecting the cladding to be perfectly flat. So there is going to be some tolerance issues there we need to accommodate for. You might actually see a larger cavity designed for things like brick, where we're expecting a pretty decent amount of mortar buildup. Mortar can fall in that cavity and really block it. So larger cavities are typically designed for things like that, just to accommodate construction tolerances in the field. All right. So we can spot the drain flow or the drainage and airflow paths here. In this case, it's the vertical furring or hat channel, whatever that is, that's going over the horizontal members there with the exterior insulation. Right, that vertical space is what is our drainage and airflow path. Here it's just the cavity behind the brick veneer that's in between the brick ties. That's going to be our airflow and drainage path. And then here it's actually the vertical wood furring strips that are fastened over that exterior foam insulation. Okay, lots of different ways to create this cavity. But again, you got to think about not just the assembly, but all the details, right? We've got in this particular wall, we've got, what are we doing at the base of the wall to let water and airflow out? What are we doing at a typical floor line at this through wall flashing, right? Do we have actual airflow above and below? What about at window heads? Again, we've got another flashing. We need to think about how that's going to get detailed, how it's going to drain out. And then we've got the, the parapet, the top of the wall above this, looks like a recessed balcony. Lots of different ways for water to get trapped. So we need to think about, how each of those is going to get detailed. All right. So let's talk about cladding, the outer layer. So when we say cladding, we're talking about really the non-load bearing element that forms the exterior layer of the assembly, right? So this is really just what you see. This is what's supposed to look good. So it could be stucco, could be EIFS, metal panels, brick or stone veneer, terracotta, wood siding, phenolic panels. Like there's tons of different examples. It's an exterior layer, so it's meant to hold up to UV and weather. Any of these could be used in a rain screen assembly. So you got to think about how it's going to be attached, how we're going to create that cavity behind it, the other thing we have to look at is the degree of openness in the joints is going to affect our design of the rain screen assembly. All right, so yeah, just some more examples here, more pictures. So what I mean by degree of openness, right? We've got something like a lapped siding. So this could be fiber cement, could be wood shingles. Basically, almost all the water that hits this cladding is not going through. Maybe 99% is going to not go through. You might get 1% that kind of slips in around, usually around the joints, penetrations, things like that, all the window details. That's going to be where your water gets in, not really through the siding itself. It's nicely lapped. And then you get something more like a panel cladding with sealed joints or butt joints. It's going to stop, again, most of the water from going through, but it will let more water in because it's not shingle lapped. And so that's going to put a higher amount of stress on your WRB, your other water control layer back here on the sheathing. And then you get into things like open joint or perforated claddings, which are actually they're intentionally designed with holes in them or gaps, and those are going to let quite a bit more water in, and so that is going to require enhanced detailing of everything behind it, right? You're expecting a lot more water. We need to make sure we can handle that kind of water. So the degree of openness is really going to affect a lot of decisions we make about how everything else is detailed. The other thing this can let in is not just water, but UV. And so open jointed claddings have to accommodate UV behind that cladding. So there are membranes that are UV stable. In some cases, we might want a second membrane that's right behind the cladding. Lots of different ways to do it, but you have to account for that UV as another load on your assembly. All right, and water-resistant barriers, there are tons of them. This could be a whole separate presentation, but this is really the inner layer in the rain screen assembly. This is kind of the last line of defense for water, right? We should not ever have liquid water get behind the WRB. If it is behind it, that's considered a leak. That's in our building, and that's not what we want. So there are sheet applied, there's self-adhered versions or mechanically fastened versions. There's foam insulation, either sprayed or taped boards. There's fluid applied systems. Lots of different ways to do this. Again, this could be its own presentation, but the key here is just that they're all water resistant barriers, and a lot of them are actually also air barriers, and so they are detailed to be sealed airtight. In some cases, in some assembly configurations, they're actually also the vapor barrier. So we see that sometimes where there's all exterior insulation, and that membrane, the WRB, is also it's really doing three different thing all at once. It's the water resistant barrier, the air barrier, and the vapor barrier. Backup wall structure, again, any of these could have a rain screen, right? Our kind of standard wood framed residential and multifamily assembly, right? We see rain screens used a lot with mass timber, steel framed, ICF can have a rain screen over it, concrete, CMU, really any of these, it doesn't matter. You can have a rain screen over it. What does start to matter is how it's attached. Attachment of cladding and other things can get more limited with mass walls, where you've got to use, Tapcon screws or some other kind of structural attachment to concrete or masonry is a bit more tricky than steel or wood framing. The other thing that actually does get easier with mass walls or even mass timber walls as a backup structure is you can fasten the cladding to it anywhere. Whereas, with a steel frame or wood framed backup wall, your cladding attachment really has to go into the studs. And so you're limited in terms of where you can fasten things. Whereas if you've got a solid structure to fasten to, then that gives you some flexibility in terms of where the cladding gets attached. All right, some additional components here, right? So, again, we've got our three main components, which is the outer layer, the inner layer, and the cavity. But there's also a lot of other things that are sticking through here, right? We've got our cladding attachment, structural support. This could be clips, could be girts, could be a whole bunch of different things. This is just hat channels that are fastened with long screws all the way through the insulation. That can also work. And then with quite a number of these systems, we're very commonly seeing exterior insulation. That also actually plays a role in water control as well, which we'll talk about here shortly. And then again, we talked about the WRB quite often also functions as the air barrier. So it's got to be sealed airtight. And it may or may not also function as the vapor barrier. Again, this depends on the climate, where that vapor retarder layer is. Could be on the outside, could be on the inside. That's going to depend on the climate conditions. The air barrier is required by code, and it could also be anywhere. It could be on the interior, it could be on the exterior. It just has to be somewhere in the wall. Okay, so cladding attachment, right? We've got cladding attached directly through the cladding into the cavity. This is common with panel claddings, for example. Those are quite often attached all the way through, or sometimes they're attached into furring first. But when we have exterior insulation, we want to try to reduce the amount of metal or conductive things that can stick through that insulation. So this is showing metal girts sticking through the insulation. This is kind of an old school way to do it. This really devalues the thermal performance of that assembly. We want to have ideally no or minimal thermal bridging through that exterior insulation. So we use things like thermal clips, like fiberglass or high density plastic. There's a lot of different ways to do it. Right, so here's kind of the more old school ways with metal girts, either vertical or horizontal, going through the insulation. This image on the right here shows a double girt approach, which is also possible but very expensive. But these all perform relatively poorly thermally. So what we've gotten into now is more modern systems, which involve all sorts of clips and rails, or sometimes continuous fiberglass girts. There's probably a few dozen of these now from different manufacturers, where the goal is to limit the amount of thermally conductive material that goes through that insulation. Lots of different flavors of this. Some of them are I would say better thermally than others. Some are better structurally than others. Some are better in terms of fire performance than others, but tons of different ways to do it. Yeah, so there's the clip and the rail, right? And there's usually some adjustability built into these, which is nice. So you can overcome walls that aren't perfectly flat. Again, lots of different ways to do it. But this is what codes are moving toward with insulation requirements, is not just shoving metal girts through your insulation everywhere. So the other thing exterior insulation does for us, not just thermally, but it really helps with water control. This is just going back to that open joint assembly here, right? We're going to get a lot of water going through the cladding, but if we now have this layer of continuous exterior insulation, it's going to act as another water shedding surface, right? If we've got like a foam board insulation or even mineral fiber insulation here, the exterior mineral fiber insulation, I think all of them have some kind of water repellent coating on them that's actually going to shed quite a lot of water. And so the amount of water that actually gets back to this membrane on the wall is very limited, which is good. So that's what we want, and that's just another added benefit of this exterior insulation. There are a lot of different types of exterior insulation, and there are some important design considerations that need to be accounted for, right? There's number one, it's in a wet space, so it has to be able to get wet. So you're limited there to either mineral fiber or foam board insulation, whether that's EPS or XPS or polyiso, or spray foam, so medium density spray foam, closed cell foam. That's another option there. But then you also need to think about vapor permeability of the exterior insulation. So this is going to impact how the wall is going to perform and manage water. So things like foam plastic are going to be much lower vapor permeability than mineral fiber. But again, lots of different types here. And they have also not just different permeability, but different thermal performance. So different amount of R value per inch. And they also may have, well, they do have quite a bit different properties in terms of combustion and smoke development. So that's another thing that needs to be considered there for exterior insulation. All right, so if you're anything like me, I'd love to go or drive around town and look at job sites and just kind of see how they're building things. But right here we've got mineral fiber insulation here that's in between a clip and a rail system. This picture we showed earlier, this is a polyiso rigid foam insulation. It's actually got a foil facer on it. And then this is closed cell spray foam in between a clip and rail system that's horizontal. So again, lots of different ways to do it. It's always fun to take a look around town and see what people are building with in your area. All right, and then we've got the air barrier system. This is another really important part of the enclosure, and this is what controls air from flowing in or out of the building enclosure. So we don't want air to be uncontrolled moving through the envelope. It can transport moisture with it, create condensation problems. It's basically, outside of bulk water control, I would say the most important control layer in the assembly. It stops heat loss. It stops pollutants from coming in or out. It helps with acoustics. Lots of benefits to having an air barrier. And it needs to be continuous around the whole building envelope, whole building enclosure. So again, they improve resistance to water intrusion, improve indoor air quality, reduce energy use, all that good stuff. So anytime you're separating interior and exterior space, you need to have an air barrier. It says always recommended or required by code. I believe it now is required everywhere by code, at least in North America, or I should say Canada and the US. It's required everywhere. and it's not going anywhere. So we need to have air barriers. The good news is they can be anywhere. It's not climate specific. All they're doing is stopping air. It's not the same as a vapor barrier where it is climate specific. So air barriers can be on the outside face of the wall. It could be the inside face, or anywhere in between. Lots of different ways to do it. Quite often there's actually a couple of different airtight elements in the wall, right? You've got your primary air barrier, which is, has to be airtight, and then you've got other stuff in the wall assembly that is mostly airtight, but probably not perfect. This could even be like your interior drywall or your interior vapor retarder that typically doesn't get sealed quite as well as the exterior membrane in a lot of cases, but you have to have it somewhere. And then the vapor retarder or vapor barrier, these are terms that are conflated that actually mean slightly different things. But its purpose is to limit water vapor diffusion across the wall. So lots of different things will do this. Its position, where it's located in the wall, whether it's interior or exterior, is climate specific. It's also dictated by where the insulation is and what the indoor conditions are. And so there's not one size fits all solutions here. You actually have to think about how that whole wall assembly is going to perform hydrothermically. All right. So again, let's take it to the streets. Go look at buildings around you that are being built. Try and figure out where the rain screens are, what insulation they're using, whether they've got a separate air barrier, vapor barrier. This is something I like to do. I always look at construction sites whenever I'm traveling anywhere. Lots of different variations between different locations, how they like to build things. But yeah, let's wrap it up here. So just summarizing rain screen assembly, right? It's those three minimum components. You got your outer layer, which is the cladding, your inner layer, which is the WRB, and then the cavity between that is there to have sufficient removal of not only liquid water, but also water vapor. And yeah, so some key takeaways here, and we'll have some time for questions at the end. So really, the main benefit is that it effectively manages water, which increases the building's durability and resilience. It allows for a lot of opportunities for exterior insulation, so adding that energy efficiency component. It's an assembly, right? It's not just a system by itself, but it's the whole assembly that has to be put together. And it's going to give us safer and healthier buildings, and then give us the design freedom to make it look like whatever we want. Lots of different ways to make it perform. And there's many different products and materials and systems that can be used to achieve an effective rain screen wall. So that's what RAiNA is here for. We're here to help. We've got lots of different technical bulletins, resources on our website. We do training sessions like this. Happy to help out if you've got rain screen questions. We're here to answer them. So with that, that's all I've got. I will jump into the questions now. Tao, are there questions that have come up during the presentation that I can answer?
Yes, there's a couple that just came in. So is a rain screen wall required under every cladding, or is it optional?
I guess I should, it depends on where you are. There are certain codes, local codes that do require it. They're actually required in all of Canada, but I would say it's almost always good practice. I mean, the one scenario where they're maybe not 100% needed is if it's a super dry climate. It's because they're really all about managing rainwater. But I mean, even in dry climates, you still get rain. There's nowhere on Earth that it, or at least nowhere in the U.S. that it doesn't rain ever. So they're always a good idea. Whether or not it's required is going to be code specific, and I can't tell you exactly which local codes have language in there that requires a rain screen.
So what is the difference between an air barrier and a water barrier? Can you give some examples of air barriers?
Sure. So I will say that in most modern construction, the water barrier that you're putting on the outside of your sheathing is going to be also an air barrier if it's detailed that way. So this is like your house wrap, anything like that. If it's taped and sealed at all the joints and penetrations, it will also function as an air barrier. The exception to that is like if it's like building paper, that's just lapped but not sealed. That's not going to function as an air barrier, even though it will shed water. The water barrier is really, it's just that it's to shed liquid water. So the air barrier is quite often the same product. So any of those like self-adhered membranes or anything like that, those are going to function as an air barrier as well as a water barrier. You do sometimes run into interior air barriers where they actually are sealing, the drywall or sealing, a vapor retarder on the interior side of the wall, making that into an airtight layer. The air barrier is just a description of what is the most airtight thing in your wall assembly. And quite often it's going to be that exterior membrane, but not always.
Thank you. So before you mentioned face-sealed eaves, which is barrier eaves, earlier in the presentation. So that system hasn't been used or not as often in the last 30 years, and has been replaced with drainable eaves, which includes drainage. How would you classify that cladding?
So drained eaves, I would say it drains quite well. I don't think it ventilates very well. You could maybe make the argument that it is a vented system, but not ventilated. It depends a lot on how the flashings are detailed, but you really don't get a lot of airflow behind there. But they do drain. So I would call it kind of somewhere between a concealed barrier and a drained but maybe not ventilated assembly.
Thank you. And then what are some recommendations for ventilation and drainage for something like stucco?
So yeah, stucco is a great cladding material, but we all know stucco does crack over time. So in terms of water management, it also it cracks, it can absorb water, and so it's a great idea to drain behind the stucco and ventilate it. And that's where we see a lot of those drainage mats behind stucco with a lap over it, so you can let water and air drain out of the wall behind the stucco. Also seen stucco in like a exterior insulated assembly where there's basically thermal clips and insulation, all that stuff, and then they'll actually fasten cement board or some kind of rigid substrate over those girts, and then apply the stucco to that. So you actually have a cavity behind it with exterior insulation that can work as well.
Perfect. So that concludes our Q&A session. Do you have anything else to add, Denali?
Nothing for me. Thanks for coming, everybody. Looks like we finished 5 minutes early. I'm surprised there were no questions about air barriers versus vapor barriers, but hopefully everybody got that they're not always the same thing. But yeah, thanks for coming, and hope you check out RAiNA. And if you're interested in joining RAiNA. We'd love to have you. We've got a lot of different committees talking about all sorts of different Rainscreen related things. If you want to contribute, we'd love to hear from you.
Well, thank you, Denali and RAiNA, for this informative presentation. Thank you, everyone, for attending. Check out awci.org for more upcoming webinars. Thank you, everyone. Have a good day.